Z-tests. All right. So we finished last week, and this will actually be a review for the quiz today, so that'll be good. Which we'll stop early to do. So we finished last week with Z-scores and Z-tests. But we didn't really call it Z-test yet, so I'll explain what all that is today. So kind of a quick review. Chapter 6 and Chapter 7 I kind of merged together. So if you're reading these in the book, 6 is actually really short. 7 is most of what we did last week, but we're going to review some more examples. So if our population mean is 10, so this is mu, is 10, and the standard deviation, that's sigma, is 2. What is the percentile rank? So we're trying to get percents of a group with a sample mean of 6 versus a sample mean of 11. So this was one of the ones where I first have to convert to Z, and then I have to use P norm, because this is percent. So for the first one, our Z score is going to be 6 minus 10 divided by 2. There's no standard error because there's no people. This is one person at a time. Oh, so I said a sample mean. I probably should have said one person's score. So let's try that. Let's make sure this is clear. This is X. I made these nice and easy. -2. Half. So what I would do is put those into Studio because I could estimate on my own. So 2 is pretty easy, right? Because of the 34-14 rule. So the first one is 0. So this is going to be 50. At 1 here, it's 34-14, 2. So they're asking for percentile rank, which means they want to know up to this point. So it should be about 2%, which also means we want lower tail is true. So let me blow this up so you can see it. Plus, yeah, no, thanks. Okay, so P norm. Again, you can use the regular computer. There's nothing fancy to install. So probability of a -2, right? And then our lower dot tail. This time, because we're asking for percentile rank, we want it to be true. So we got 2.27. Now a half should be half of 34. This is 1, so a half here should probably be about 17 plus 50, it's about 67%. Half of 34 is 17, yeah? Yeah? Yes, okay. So let's try P norm, 0.5, lower tail equals, still true, we still want percentile rank. Okay. So 69%. So the 34-14 rule is really to just get you to kind of be able to estimate, to make sure you're plugging in the right numbers. But now the question is, what percent of samples would score higher? Well, that's just the opposite question. Sorry, this is 69. Wait, something. 1. So which samples would score higher? The only thing we'd have to do is change lower tail from true to false. And this adds up to 100, so we could just subtract. But I've said several times I don't like to think that hard, so I'm going to do the math for me. So 98 or 97.7% are going to score higher. And then 30.8% are going to score higher for this group. So percentile rank is the lower tail is true, because we want everything up to that point. If we want to score higher, lower tail is false. Yeah.
For the test, how far should we go with those decimals?
Oh, 2 decimal places is good.
2 decimal places?
That's, I think, what it does on the multiple choice, if you're looking at it online.
Oh.
Sometimes they totally round to, it might just say 34%. Kind of depends. If they're asking you about the 34-14 rule, or they tell you to estimate, they're going to round. But if they tell you to look it up in the table, we're just using this as the table, then it's going to be 2 decimals. Yeah. But the book does almost everything in percents. And then, but p-norm gives you proportions. So just multiply by 100. Okay. So moving from one person to a sample, really very, very few times, at least in our research area, that we're going to do one person at a time, unless you're doing single subject designs, applied behavior analysis. And so we're not really spending a whole lot of time on just like one person. Instead, we're going to do multiple people. So we've got to use this standard error formula. Remember, this was the Oprah of standard deviation. So you get some and you get some. The standard error is supposed to estimate the standard deviation of the sampling distribution. That's the skinny one that has lots of samples in it. So we've got an average test taking time that's 22 minutes. So anytime they talk about an average time, they're talking about mu. If the average time for everybody is 22 and a half, that's mu. After you look at several of these, you'll see where they differentiate between the sample of people and then the overall averages. The standard deviation is 10. Here's another hint. If they're in the same sentence, they're both the population. My class of 25 students, so that makes N 25, took 19 minutes. Seconds, that would be amazing, but no. So, oh, I already did this for you, but population mean is the 22 and a half. Population standard deviation, sigma is 10. I have to have N here in a second. My sample mean is 19, and we don't have standard error. So standard error is going to be sigma over the square root of n. So 10 divided by the square root of 25, which is 5, which is 2. It's very easy for me to make a math mistake because I do rely on computers so much, so just let me know, like, yo, Dr. V, that's actually 4 if I'm wrong. So now I have standard error. And the question is, what percent is above me and what percent is below me? So the first thing you have to do is do Z. So now we have mean minus mu divided by standard error instead of just standard deviation. Because I've got to account for this is 12 people, not just one person anymore. So I got my 19 minus 22 and a half. Divided by 2. Okay. That math I can't do in my head. 3 and a half divided by 2. $1.75. So if I'm at a negative 1.75, this automatically is 50% of people. And we're trying to figure out how many are above my class average score and how many are below. So again, we're still doing percentiles, so it's p-norm. Remember, what goes in p-norm is always the z-score. So if you try to put in the mean, like 19, it'll give you a p-value that's very, very small or very, very large. That's a good clue you've done something wrong. So negative 1.75. For, whoa, caps, there we go. That should be a comma, not a period. There we go. For how many people are below me, that would be true. Okay. If I think about it, at 2, it's 2%, so this would be slightly over 2%. Okay, it's 4%. Right on the money. That makes this 46. So the other way should be 96%. Okay. They do add up to 100, but if you aren't sure, you can do lower tail equals false for above, and it's 95, 96 rounded up. Now, specifically to this question because of the way it's worded. So if the average test taking time is 22 minutes and my class scored 19, my class is actually doing this faster, right? Yeah, we're going faster, but that makes my z-score negative because my z-score is lower than average. So this doesn't necessarily mean that my class is worse than their class. You have to think about the context of the question. So my class is doing the test faster, which means their scores are lower. So anytime you're dealing with time, be careful, because lower scores don't mean worse. Sometimes they just mean faster. Or if you're trying to decrease, maybe do a weight loss program or a smoking cessation program, lower scores are better. So think about the question. There's always one, I can't remember if it's still in there or not, that really tricks people up. They're like, so-and-so's doing better. I was like, that means they're at the hospital longer, which is not better. But their z-score is higher, yes. So yeah, my z-score is less than the mean, but think about what that implies. All right, one more. And then the ones on the quiz are actually a little easier than this. So we make everyone take the major field test. If you're a psych major, it happens in Psych 411. So that we can show that you've learned something, hopefully. So Baylor wondered how their students were doing. So they reported a mean on a standard deviation of the population. So this is the number just to throw you off. That's the population size. So the mean overall, so mu m is 156.8. The standard deviation of 14.6. If they have 36 people in their department who took this test and got 164.6, should they be celebrating? So basically, is their score higher? And when we're getting to a z-test, that'll tell us whether or not it's significantly higher. Right now, we're still talking about percents. So we've done all of this except standard error. Ooh, sigma. It's Monday. There we go. So we're going to take sigma, 14.6, over the square root of n, 36. So 14.6 divided by 6, 2.43. And we're going to see how many people are above and below their score. So their z-score is going to be positive because they're doing better. So their score, the mean minus the sample mean, divided by standard error. And don't forget, R is a calculator, so you could use it to calculate this, but phones are just as handy, right? I pay all this money to calculate things on my phone. 3.21. Remember, I said before that z-scores over 3 are pretty unusual. So their score is going to be very high. So here's 0. 50% over here. And then we're trying to figure out where's 3 out here. So we have 34, 14, and 2. Where is the 2 on the 3 part? Does that make sense? That sounded very, it's probably going to sound very weird online, but like, what part of it cuts off at the 2% right here? Yeah. So there's 2% above 2. Where does 3 fit into there? So let's try that. I keep wanting it to be p-rom. I don't know why. There we go. So 3.21. Which one was first? Above. So above would be false. So even if I multiply that by 100, it's 0.06, 0.07. So there's only 0.07% of people's scores above them, which means they're at the very top. Okay. And then if I wanted to do below, again, you could just subtract 1, but it's 99.93% are below them. So anything past 3 is just really at the very, very top of the very, very bottom. So if you get a z-score of 12, it's probably wrong. Sometimes I'm bad at making up the examples, but I was trying to show that kind of z-score is really, really high or very low. All right, so that's kind of a summary of what we did last time, where we talked about how do I calculate z. The only thing we haven't repracticed is how to calculate x. Right. Yeah?
Is okay, when you're dealing with standard error, because you're dealing with a larger population, is a standard deviation, so I guess it's a z-score that's over 2.5, basically not going to happen? Because, I feel like if it's an individual, I can see it happening, but
right.
With a group.
Yes, your group score would be very, very different. Past 3 for sure, but we're going to get to probably Wednesdays. Anything past about 2 is really unusual. Yeah.
You'd have to be like college professors.
It'd be really high.
Yeah.
Or really low, either way. Yeah. So the odds of getting scores that extreme are fairly low, which is the point of hypothesis testing. All right, so now what? What's the purpose of all this stuff so far, other than percentiles, like the obvious application to testing? Right. So we have all of the ideas for hypothesis testing, and now we're actually going to try it. So we've got hypotheses. We did those 2 chapters ago. Null versus research, or levels, or groups, or variables. So I think on the chapter 5 homework, you had to write some hypotheses. We talked about distributions, so that's what we've been doing now. How do I compare scores? This is z-distribution. We've got p-values, that's the percentile stuff. And I want to say it was chapter 5 that also covered rejecting and failing to reject a null and what that means. So how do we bring all of this stuff together? And so that is what is on this worksheet. The only thing, no, it has it all in here. It's like this is what we're about to work through. It's this worksheet. And so we're going to work through each step one at a time. So this is hypothesis testing, but it runs this way, not down, but across. So when you go to work on your homework and stuff, you will not get this on the test, but I promise by the time you've done about 10 of them, it's not. It's pretty easy. But that will help you study. The first step was always to talk about assumptions. So when I teach my advanced class, which is right now, that's the first thing we always do is we talk about data screening and assumptions. So do I even have the right type of data for what I'm about to do, like statistical analysis wise? And does my data meet this rule that I have to have? Okay. So assumptions, accurately named, are things that have to be true for your statistic to mean what you think it means. So sort of conditions that are necessary for your statistic to be accurate. Because there's plenty of garbage in statistics. And if you feed in garbage, you're going to get out garbage. So you have to test to make sure that the stuff that you have isn't a mess. So in my graduate courses, in my upper level courses, we go through like, how do I check and make sure the data is accurate? How do I check this and this and this and this? What we're going to talk about is the more simplified version. But it's this idea of like checking to make sure the data meets the rules for this test. Which gets me into parametric and nonparametric, which we did at the very beginning of the semester, I think, but now it will hopefully make more sense. So we're into inferential stats, moved away from descriptives. And parametric tests require assumptions. They're more strict, they have more rules, so they're like your mom, I guess. Straight, they're really strict. Non-parametric tests have less assumptions. They don't not have any, but they're much cooler. His dad. I don't know. In your family, it might be the other way around. Definitely for my mom, strict. Dad, not so much. So, parametric tests are rules. Have all these rules. Non-parametric tests have less rules, and they're slightly different. And so what happens is, if you don't meet the assumptions for a parametric test, you're supposed to do the non-parametric version. We're only going to cover one non-parametric test in this class, just because we kind of keep the material the same across classes, and that's chi-square at the very end. The rest of everything we're going to do is parametric. It's much more popular. So that's Z, T, and over regression. Basically, this whole class is parametric class. And we're just going to do 3 baby assumptions. And this is specific to z-tests. First one is that the dv is scale. Oops, spelling. So the dv has to be at least scale, meaning ratio or interval. So can I break that assumption? Not really. So interval can get kind of tricky because those scales tend to have more problems with skew and kurtosis. But that's okay. Remember with the central limit theorem, that distribution bunnies video. But you definitely cannot have a nominal or an ordinal variable. Okay, so you have to have at least a scale variable for a z-test. So you'll, if you're working one of these, you'll say the dv is scale, and it'll say yes or no. Right. And generally the answer to this is going to be yes. Or you're done. You would have to do something else. Second one's random selection. Oh boy, that's no good. All right, we've talked about that's not a thing that we can do. Don't put a little sad face next to it. So random selection is something we generally have access to or can do. We've talked about that a couple times. Can I break that assumption? Well, I pretty much can't ever meet that assumption, right? So you can if you can do random assignment. So I can randomly assign them to groups. Okay. So if I can randomly assign, we're okay. If I can't randomly assign, because let's say you're using gender, can't randomly assign you to gender, I would just have to be careful in my generalizations. So what does that mean? It means that I can't just say gender causes this, because I didn't assign you to gender. I can't make that causal connection. So most people agree that smoking causes cancer. Well, we haven't really forced people to smoke and other people not to smoke and then tested them because that's not ethical. They have done it in animals. So we just have to be generalized carefully. Smoking appears to be linked to cancer would be the more appropriate way to say it. That's why there's always these big debates over violent video games. So we have to be careful with generalization if we aren't randomly selecting and we aren't randomly assigning. And then the last one, which is the one we have the most control over, other than our DV, is that the distribution needs to be normal. So the sampling distribution is normal. Can I break that? Well, if n is greater than 30, I don't have to care. Whatevs. Because the central limit theorem kicks in, and it's fine. Okay. So that's what the video was over, where it showed that it was just showing the idea of a central limit theorem, but 30 is about the place where we can assume that it's normal. If n is less than 30, we have to just be careful. So you either have to be told it's normal, or if we were in a different class, I would tell you how to test it. So we're really not going to go over how to test this particular issue of normality, but you could create a histogram and look at it. Right? Is it roughly unimodal and symmetric? And there are other ways to like very specifically test, is this normal, is this not? But if you get the idea of like if n is greater than 30, I don't even have to care. If n is less than 30, I do have to care and be careful. Yeah.
Does this become a problem like the less than 30 when you have like, you may have a ton of people taking your test, but it is a ton of different levels? Like, because you would have like...
Right, so in theory, 30 depends on who you talk to. So if groups are equal, 30 overall would be okay because they're essentially the same distribution. But if you think that groups are not equal, you should have 30 in each group. Yeah. So 30 is just, I always tell students when they ask me, how many participants do I need for my thesis? I'm like, at least 30. I'm like, yeah, I know, but like, we kind of like, get used to me saying 30, 30, 30. Because mathematically, the law of large samples helps us out. All right. So that, let me get, these 2 slides, and then I'll give you time to take the quiz. Wait, where am I at? Can I break it? Okay, last one. So what's this idea behind breaking these rules? The cool thing about hypothesis testing is that most of the tests are fairly robust. And what robust means in this sense is that it will still give you an it's Monday. Accurate results, even if you didn't quite meet the assumption. So that's why there's this like, be careful, be careful. It's because the test is fairly robust to violations, just the way people say it, which means that like, math is still pretty accurate. You just have to, when you're writing it up, acknowledge the fact that you didn't randomly assign or randomly select, and you don't have quite 30 people. So people can interpret it correctly. So the be careful part's basically be sure you write it up this way, because they are fairly robust. So we should still get pretty accurate results. We have bent assumptions, like, thankfully they're very flexible, because there are plenty of times that we've had tests that we didn't hardly have any of these met, and it still worked okay. All right.